All right, hello. I'm Colin Suter, and I'm going to be introducing you to the absolute zero law. So before we can get into that, first we need to understand the basic concepts of the laws of thermodynamics. So firstly, there is the zeroth law, and this law states that if two bodies are in equilibrium, they will come to the same temperature. So if there's two objects, a hot one and a cold one, then if they are in contact with each other, then the heat will transfer from the hot to the cold one. Next, there is the first law of thermodynamics, and that states that energy cannot be created or destroyed. So that means that energy is conserved in every task, every process, every transition of sorts. So energy is not lost, it is not gained, it is conserved. Next, there is the second law of thermodynamics, which states that the total entropy of the universe will increase with every spontaneous process. So, quick overview to summarize, I guess. If you don't know what entropy is, it's basically the disorder of a system. It's the number, or more officially, it's the number of possible orientations of a system. So, in every process, unlike energy, entropy increases. Finally, there's the third law of thermodynamics, which states that temperature is absolute zero when entropy is zero. So all this means is that particles exist in space. So if there's no randomness in the particles, that means that the particles are not moving, therefore they cannot have a temperature. Because as we know, temperature is just a measurement of a representation of the particle's average kinetic energy. So we can see that with this graph here. So if we were to graph the temperature of an object relative to its pressure with all other conditions remaining constant, we could extrapolate it back out to the origin. Where pressure is zero, this should be the absolute zero, which in our case is negative 273 degrees Celsius. So finally, for this lab, we will be referring to the ideal gas law. This law states that pressure times volume is equal to the number of moles of gas times a constant times the temperature of this gas. So it's important to note that the ideal gas law, as its name suggests, is ideal. It only works in these circumstances. In most instances, the ideal gas law does not work in practice, and there's a correction factor for that. But in this instance, we're just going to try and keep it as simple as possible, and we're going to use the ideal gas law. All right, so here we are again. We just want to validate why are we doing this experiment? What is the purpose, so to speak? So all that is we just want to confirm that absolute zero is what we say it's be. So absolute zero has been generally understood to be negative 273 degrees Celsius. So this experiment is just one way to prove experimentally to students or any others with concerns that this is the actual value.
This is the lab material section of this experiment. So we have a hot plate. This is going to be used to heat up our first beaker of water. We're using this water to change the temperature of our second beaker of water, which is currently room temperature. As the experiment goes on, we'll be slowly changing the temperature of this room temperature water through using this pot of currently heating up water. So then what we have here is that we have our second beaker, what we're going to be measuring the pressure of for our experiment. So in here we have a stopper, which will be used to maintain a constant pressure. We'll be holding it like this. It's important to make sure that the stopper is firmly in so the pressure doesn't change. What we have here is it's connected to a probe, a gas pressure sensor right here. So this is essentially to tell us what is the pressure inside here, giving us an exact numerical number for it. And then what we have here is we have cup holders. So our cup holders are used for holding the pot because it's very hot and we don't want anybody to get hurt. Then what we have here is our temperature sensor. So that will be used to measure the changing temperature of our room temperature's beaker as we continually pour in more hot water. And so then if we can look over here on this side is that we see we have our Logger Pro. Logger Pro is a data collection program that is essentially used to showcase, graph and analyze our data for us. So we'll be able to find a pressure and temperature graph and find the absolute zero function.
Okay, for the procedure of this lab, you first have to heat up a beaker using a hot plate and make sure you use the gloves to not get burnt. and use 2 beakers, one for heating up and one for pouring in. And the one that you're pouring in already has water in it. And you put the Erlenmeyer flask with the stopper and the temperature probe into the beaker and the pressure probe into the stopper that connects to the Erlenmeyer flask. This way, whenever you record the temperature depends on the amount of surface area that the water in the beaker touches with the Erlenmeyer flask. So basically, you have to keep the Erlenmeyer flask the same volume at where it is, or else your pressures will fluctuate. And whenever you are recording the data, make sure that the pressure is constant around there. So if it is constant, then you record down the temperature, and you do this for 5 trials. For each trial, you will pour the boiling water into the beaker that you're testing by just little amounts. And make sure that the water does not overflow, or else it will be very difficult to match with the measures on the Erlenmeyer flask to keep the pressure constant. Also, whenever you hold the Erlenmeyer flask, make sure that you do not touch the stopper, or else you will change the values of the pressure. So any touch or movement of the stopper will slightly change the pressure, and that will offset the data.
There's 2 ways in evaluating and analyzing the data. One way of doing it is by utilizing LoggerPro and its LabQuest software to collect data real time as you conduct the lab experiment. However, without the lab apparatus on hand, it's physically impossible to do this. So instead, my group members conducted the experiment and recorded the data themselves using the temperature and pressure readings given in LoggerPro and plotted the data points to find the linear regression line. Now let's try to plot the regression line. I'm going to start out by renaming the 2 variables x and y to pressure and temperature. Double-click the x column in the dataset table to edit its labels and units. The x-axis is the independent variable, so in this case, we will make it pressure in kilopascals. The y-axis is the dependent variable, so in this case, we will make it temperature in Celsius. Now, just simply insert the data points into the table. I'm going to be using my data points from my experiment. After plotting all the data points, go to the Analyze tab on the top navigation bar and then click Linear Fit. When graphing our raw data into LoggerPro, we noticed that there was a direct relationship between both temperature and pressure. That is, as pressure increased, temperature also increased at a constant rate. We graph the data as a temperature versus pressure graph, as it is much easier to determine the absolute zero from the experiment by utilizing the slope-intercept formula determined by the linear regression. The graph was linear, so it was expressed by the equation t equals mp minus b, where b was the slope-intercept and where it was also the absolute zero in Celsius. In our case, it was negative 291.93 degrees Celsius, where T was the temperature of the water that surrounded the flask in Celsius, and P was the pressure inside the flask in kilopascals.